Hello, everyone. So first, I would like to thank the organizers for putting up together such a fantastic program, and I'm very glad to be part of it. Thank you for joining me this morning, and I'm delighted to be here to share with you some of my recent research on large VARs. I got into this area, started working on this area only a few years ago. What attracted me in the beginning was that there was, and there still is, a lot of excitement in large VARs. As we get more and more data, this class of models I thought would be going to be more and more important. And even today, we already saw a couple of presentations using large VARs. So this class of models also present some very interesting challenges. So I thought with my particular skill set and interest, I might be able to help tackle some of the challenges and contribute. So this talk is an overview, very much an overview of some of the things I have learned in the process. As I'm sure many of you are intimately familiar with VARs. In fact, I see a lot of main contributors here in the audience. VARs have become the workhorse model in empirical macroeconomics since the seminal work of Chris Sims. We are going to hear more from him on structural VARs tomorrow. Today, I would like to focus on large reduced form VAR. There's a growing need to include more and more variables in the analysis. Partially, that could be that the applications demand you to consider a lot of variables, right? If you are interested to study the interconnectedness across countries or across states in the US, for example, then you would need to consider all the variables in the states, right? Sometimes you might be interested to study contagion in a network setting. For example, band network, then the application would require you to at least include most of the major bands. So there are a few applications, examples you would need to consider a lot of variables. Sometimes you might be only interested in forecasting one or two key variables like GDP, growth, like some of the applications we have seen today, or inflation, right? In those situations, you might still wonder whether adding more variable would improve forecasts. So there's actually quite a lot of work now that show adding more variables would help forecasting. Now, of course, just because you have a lot of variables does not mean that you have to use VARs, right? One very popular alternative is vector models, and we also have seen quite a few applications today in the morning. And here, I would argue that VARs would offer some advantages. Of course, that's perfectly fine to use vector models, and I feel VARs would complement some of the shortcomings of vector models. One advantage of using VARs is that over the last 2-3 decades, there are a lot of developments in the VAR literature, right? There are specific models designed for a certain type of data to capture certain type of data feature, right? So we have some steady state VAR, regime switching VAR, even a vector augmented VAR, VAR with time varying parameters, stochastic volatility. So there are lots of varieties you can choose from. So if you use VAR, you can tap into this large resource. Another main advantage of VAR is that there are also a lot of accessory or machinery developed surrounding VARs, right? One huge literature now is the development of credible identification schemes to identify structural shocks, right? If you use VAR, you can also tap into this literature, and you can compute impulse responses, various forms of decompositions. So those are the two advantages of using VARs. So I would arrange my talk around 3 different themes. First is I would talk about shrinkage priors. especially hierarchical shrinkage priors for large VARs. VARs, of course, tend to have a lot of coefficients, and if you have a large VAR, especially so. If you have some of the non-linear extension, like some regime switching VAR, for example, you would even double or triple, or how many regimes you have that multiple times of the VAR coefficients. Right? So even if you have a 30 variable VAR, the VAR1 coefficient matrix is going to be 900, and if you add 4 lag, you very quickly get into thousands of coefficients. So in this setting, large VAR setting, shrinkage or regularization is the key to make this model works. But of course, if you have some more flexible shrinkage, you also add a lot of latent variables that would also make computation even more intensive on top of all the coefficients you have already. So second theme I would like to talk about is stochastic volatility. So the last decade or two, one of the most robust findings in the literature is that adding some sorts of time varying volatility is empirically important. It often helps not only help fund forecast better, but also density forecast. So there are actually quite a few stochastic volatility specifications designed especially for large systems. But of course, if you add some of the stochastic volatility, it would also make the estimation more time consuming. So that brings me to the third point, the third theme about some fast algorithms to estimate these large nonlinear models. So I would like to share with you some of my experience in this area and some of my discovery. How do you make the estimation faster? So those are the three themes of my talk. So the first one, I would like to start with shrinkage priors. And in this area, the most prominent class of priors is Minnesota priors, tracing back all the way in the 80s by work Littleman and Sims and various co-authors. So in the original version, that was before MCMC, right? So they in the original setup, they assume the covariance matrix to be fixed, and you don't really need to do any estimation. And then later on in the 90s, the second generation, people realized estimating error covariance matrix actually helps the forecast better. But that was also, you need to use already MCMC, some simulation method. And the third generation, more recently, we realized you can actually even improve the forecast performance even better by estimating some of the key hyperparameters. So those are the shrinkage parameters. So if you estimate them instead of fixing them as some subjective value, you can actually improve forecast quite a lot. So this, I would say, probably the most prominent class of models. There are lots of Minnesota priors. They have enjoyed great success, but the last decade, also a few years, these Minnesota priors have been criticized for not being adaptive enough. So essentially, they are all Gaussian priors. So the tails of the Gaussian distribution are thin. So what they tend to do is to shrink both large and small coefficients, and theoretically, that is not something you would like. When I first started in this area, I actually went through a lot of different versions of Minnesota priors, because there are actually quite a lot of them. Right? I talk about 3 generations, there are a lot more. And I try to figure out what would be the most important features of Minnesota priors, right? So what I found is that the 2 features are most important are cross-variable shrinkage. This idea that you want to shrink the legs of other variables more strongly to 0 than your own legs, right? So if you are in the inflation equation, you would think that coefficients on other legs, such as like some money or unemployment, tend to be on average smaller than past inflation, right? So this cross-variable shrinkage is quite reasonable, and empirically that actually is also quite important. So in my talk later on, I would have two key parameters, kappa 1 and kappa 2, that control shrinkage strength for own versus other legs. Kappa 1 for own legs, kappa 2 for other legs. So when kappa is smaller, then that means you shrink those types of coefficients more strongly to 0. So this cross-variable shrinkage is actually in the original version, but later on, due to computational reasons, some of the Minnesota priors, they don't have this, especially when you use natural conjugate prior. Because of the nature of the prior, you cannot have this cross-variable shrinkage. Sometimes people don't use it. So another feature is important is database hyperparameters. So instead of fixing kappa 1 and kappa 2 to some fixed value, it's actually quite important to estimate them. There are actually quite a few papers pointing this out. I suppose it's also quite reasonable thing to do, right? Because now we are using VAR for a lot of different purposes, right? So you have different time period, countries, frequency, and so it's reasonable that one set of hyperparameter might not fit all of these data sets. So it's useful to estimate them. So here, this is one of my favorite graphs in a paper of mine, asymmetric conjugate prior. So basically, on the right panel, that is a joint posterior density of kappa 1 and kappa 2. Remember, kappa 1 is the shrinkage strength for own leg, kappa 2 is for other legs, right? So what it shows is that the high posterior density is around, for example, kappa 1 would be, say, 0.4, kappa 2, 0.01, right? So you can see there's a large difference if you estimate these two parameters. So they are not the same. Their order of magnitude is different, right? That makes intuitive sense because you, if you regress inflation on other variables, you would expect the coefficients to be smaller than regressing inflation on its own leg, right? So if you zoom out, so that would be on the left panel. So it squeezes this density into this like a flat pancake. And now I plot two more prior. One is the subjective prior that is widely used in the literature. So this set of values, something like kappa 1 is 0.2 square, kappa 2 is 0.2 to the power 4. It will be somewhere here. So another widely used prior is to turn off the cross-variable shrinkage, meaning that you set kappa 1 and kappa 2 to be the same, and so, but you estimate them, and it would be on the diagonal line, so it would be somewhere here. So it would be a compromise, right? So the estimated kappa 1 would be a bit bigger, kappa smaller, and kappa 2 would be bigger, right? But the point I want to make is that none of these alternatives is in anywhere near the high density region. So empirically, we found some evidence that the two key features I mentioned are important. One is cross-variable shrinkage. The other is to estimate the hyperparameters. So that's Minnesota prior. And more recently, only the last decade, there are some adaptive hierarchical priors. And in today's talks, Florian talked about the horseshoe prior is one of them is also here. So they are more flexible in the sense that they are all, well, the three I listed, they are all mixture of Gaussian, right? So the first one is the first layer is Gaussian, but the mixing variable is gamma. You can, if you have a Cauchy, half Cauchy distribution, you get a horseshoe. So all of these priors, they have much thicker tail than normal, and they also have a lot of mass around 0. Horseshoe, for example, the density approaches infinity when you go to 0. So what this prior does is that when the least square estimate is large, so it would be somewhere at the prior tills. You tend not to shrink them too much. You allow for them the possibility that some of the coefficients are very large, non-zero. But when the least square estimates are close to zero, you tend to shrink them a lot to zero. So you get some sort of sparse model. So those, they have very good theoretical properties. So I just described the intuition about that. What is a bit puzzling is that these more flexible hierarchical priors, they don't seem to forecast then a particular version of Minnesota prior. So that is highlighted in this paper by Cross, Ho, and Poon. So there are quite a few interpretations of this result. Right? One could be that maybe the macro data, they are not sparse, right? Maybe everything is related to everything else, and so we might have a model in which most of the coefficients are non-zero, but they could be very small. So maybe in that scenario, these hierarchical shrinkage priors that try to induce a sparse model might not work very well, right? Which regression might work better. But I have a different view. I think the sparsity could be one reason. Another reason could be that these adaptive hierarchical priors, typically as they are implemented, they treat all the variables identically. In contrast, Minnesota priors, they incorporate a lot of rich prior beliefs. So some of the things I mentioned, right, you have cross-variable shrinkage. You also shrink some of the higher less more aggressively. So you treat the coefficients non-identically. So that might help having a better forecast performance. And actually, some of the results I have suggest this interpretation. So both of the classes, Minnesota priors and hierarchical adaptive prior, they have advantages and disadvantages. So why not have both of them, right? Best of the both worlds. So in this paper, Minnesota type adaptive hierarchical priors, I propose this class of models, a class of priors that include both features of these adaptive hierarchical priors and Minnesota priors. So they all have very thick tills, a lot of mass around zero, but they also provide a framework to incorporate much richer beliefs as in the Minnesota prior. So in a forecasting exercise, we show this new class of priors beats the other two I mentioned. So I will just highlight a few details. It's just this prior gives you enough room to put stuff that you are interested in, right? So basically there are three things. They are all written as a mixture of Gaussian. So the first one is, the first layer is a normal distribution. And first there is this global component. So even though I call it kappa ij, so this is theta ij, theta ij is the jth coefficient in the ith equation. So if one of the VAR coefficients, this kappa ij can take only two values, either kappa 1 or kappa 2, depending theta ij is its own leg or other leg. So this global component controls the shrinkage strength for all the coefficients in the group. And then we also have a local components like in those adaptive hierarchical prior that has some sort of distribution, right? So if this psi is a Gaussian is a gamma distribution, then you will get the normal gamma prior. The third component is this Cij. So this is something that allows you to have non-identical distribution. So these values would be incorporated from Minnesota prior. So it allows you to incorporate richer framework. So this setup includes both classes of priors I just mentioned. So in the application, I focus on one class of priors, the Minnesota type normal gamma prior, and they seem to forecast better. So in the paper, there are lots of forecasting results, but here I just want to highlight the estimation result to show what I'm trying to mention. So comparing to the normal gamma prior, right? Normal gamma prior doesn't have a cross-variable shrinkage, so the kappa 1 has to be equals to kappa 2. But if you allow them to be different, then kappa 1, the shrinkage strength for own legs increases a lot. So what that means is that you don't shrink own legs as heavily, aggressively as the normal gamma prior. And on the other hand, you shrink coefficients on other legs more aggressively. So it shows that the cross-variable shrinkage, that feature is relevant here. I also want to mention that this is a normal gamma prior that includes the lasso as a special case. When nu is equals to 1, you get better lasso, and the estimates are actually very small, suggesting that lasso might be a bit restrictive. So you want to be a bit thicker tails than the double exponential corresponding to the lasso. So another result is that now I compare the Minnesota prior with the Minnesota normal gamma prior, right? So the only difference is that here the normal gamma prior has a local component. And here you can see that by adding the local component, so once in a while you get a coefficient that is large, right? So the local component is supposed to take care of that. If you take care of that, then you can apply more aggressive global shrinkage. And this is exactly what's happening, right? So compared to Minnesota prior, that doesn't have the local components. Kappa 1 basically is reduced by more than half. Kappa 2 is even a few times reduction. So these results show that both features are present, meaning the cross-variable shrinkage and the value of the local component. So that is the first theme I want to talk about, highlighting what kind of features are important in shrinkage priors. So the second theme I would like to talk about is stochastic volatility. So large VAR, there are now a few proposals for stochastic volatility. One of the very first paper, Carrero, Clark, and Marcelino paper, they have this common stochastic volatility model. I would talk about this model in a little bit more detail in a few slides. Later on, they have an algorithm to estimate more general version of a stochastic volatility. The model is actually Collier and Sargent, but they have the contribution of the paper is an algorithm to estimate this model in a very large high-dimensional setting. And there's also a paper by Kessner that consider factor stochastic volatility model. So these are a few stochastic volatility models designed especially for large VARs. So they present some very interesting trade-off between some models are more parsimonious, some are more flexible, some are easier to estimate in terms of speed. It's quite fast, but it doesn't seem to have we don't seem to have a good way to choose between them. So this paper tried to address this question: how do I compare these very different models? So this is from this paper comparing stochastic volatility specifications for large Bayesian VAR. So essentially, the core of the paper is to have this estimator to estimate the marginal likelihood, right? So while this is a forecasting conference, you can think of the marginal likelihood as just one step ahead density forecast. So it has that interpretation. You can just think of the log marginal likelihood as just the sum of log scores for the whole sample. So this paper just has a way to compute it. So in this setting, it's actually quite hard to compute the marginal likelihood because there are lots of VR coefficients to begin with, and there are also a lot of latent variables, right? If you have stochastic volatility, 100 of them, there are 100 different stochastic volatility processes. If you have factor stochastic volatility, you also need to integrate out the factors. So the paper, what I did here is come up with an algorithm to compute the marginal likelihood by integrate out all the VR coefficients by hand. Turns out you can do it. And also have this adaptive importance sampling estimator to integrate out the stochastic volatility and factors. I would not be able to go into details, but this adaptive importance sampling is something I'm excited about. Seems to be quite useful. So the idea is very simple. It's just there is a theoretical zero variance importance sampling density, which you could not use in practice, unfortunately. But what you could do is that I have a parametric family, and within this parametric family, I choose a member so that it is the closest to this ideal zero variance importance sampling, the distance being measured by Kuppert-Leiber divergence. So basically, that's a one-line summary of the algorithm. But if you are interested, I encourage you to look at the paper. So next, I would like to just very briefly go through the three models I try to compare. So the first one is common stochastic volatility, right? So here I have the use of reduced form VAR. The common stochastic volatility is just this scalar e to the power h that scale up or down this covariance matrix sigma. So this common stochastic volatility often has a natural interpretation as some sorts of macroeconomics uncertainty. So the advantage of this model is that if you use the natural conjugate prior, then estimation is very fast. You can do it in a minute, even if you have 50 variables, 100 variables, very fast. And the complexity is O(n) to the power 3, n being the number of dependent variables. So it's one order of magnitude compared to other stochastic volatility models. So it's very fast. The disadvantage is that it's seemingly restrictive on two fronts. One is that the likelihood, if you recall, there's only one scalar scaling up the covariance matrix up or down. The other restrictive feature is that you have to use natural conjugate prior. Otherwise, you don't have this computational advantage. So as you recall, natural conjugate prior does not allow for cross-variable shrinkage. And as I show in the first part of the talk, the cross-variable shrinkage is actually quite important. So that would be a drawback of this common stochastic volatility model. So the second model is essentially a parameterization of the Collier-Sargent model. Here, the reparameterization is that I write that as a structural VAR. So this A is a lower triangular matrix with ones on the main diagonal. So I want to emphasize this is a computational device. I do not commit myself to one particular identification scheme. So all of these are reduced form, right? So I estimate this model, I can recover the reduced form coefficients. So here is only a computational device. So this model, compared to the common stochastic volatility model, it is a bit slower, but it can still be estimated within reasonable time. Seemingly more flexible because now you have n stochastic volatility processes. Another advantage is that it can accommodate more flexible priors as well. In particular, you can have a Minnesota prior that allows you to have cross-variable shrinkage. So the last model, stochastic volatility model, is this called factor stochastic volatility model. So in macro, I think this is not as well used, as commonly used as the other two so far, but it also shows quite a lot of promise. Essentially, the conditional mean equation is exactly the same as before. Well, the reduced form VAR. Here, I just decompose the residual into two parts. One is the common components. I have a factor structure there. And then I have U idiosyncratic errors, and these are all diagonal matrices. So this is a pretty standard dimension reduction technique. Here, we introduce the stochastic volatility via the factor structure. So again, this model can also be estimated reasonably fast because given the factors, all the equations are unrelated, and so you can estimate equation by equation. Complexity is the same as the Koleski SV. It's also quite flexible. Maybe in certain sense, it's more flexible than the Koleski SV because now I have n plus r being the number of factors of stochastic volatility processes. Another advantage, again, it can also accommodate more flexible priors. So as you can see, there are a few of these stochastic volatility models designed for large data set, in particular large VARs, and they are very different, right? And it's not really clear which one is better than the other. So in the papers, I have a lot of graphs trying to give the reader some confidence that this marginal likelihood estimator works. So here I will not be able to show you the simulation results, but the bottom line is that the marginal likelihood estimator can distinguish the three SV models, meaning that if I generate 100 data set from a Koleski SV and compute the marginal likelihood of all the three SV, and I almost always pick the Koleski SV and so on and so forth. So let me show you some empirical results. I am interested in two dimensions. One is that that's how I started the project, is that I want to give people some tools to choose between this stochastic volatility, or maybe get some general guidelines, like what sorts of features are important when you build models, right? So I would like to compare the three stochastic volatility models. And another added dimension I want to try is try different Minnesota priors with or without these two features I mentioned in the first part of the talk, namely the cross-variable shrinkage, or whether you fix or estimate some of the key hyperparameters, shrinkage parameters. And I use data of various size to try to figure out whether it's the case that if I have a small data set, I use one model or otherwise, right? So the results are here. First, I compare the three models. So let me just say that I also compute the marginal likelihood for the homoscedastic models. But for all the data set, the stochastic volatility models win the homoscedastic VAR by large margin. So there's some sorts of time varying volatility in the data. I guess it is not surprising. So among the three stochastic volatility models, the best model is this Koleski SV. So here I call it the common SV, the Koleski SV, even though it also starts with C, but I just call it SV. And I also have the factor stochastic volatility. For all the data sizes, the Koleski SV is the best model, and often by a large margin, right? So if you compare to the common SV, that's a difference of about 100 in log likelihood, in log marginal likelihood. So that's seemingly the Koleski SV is much better than the common SV. But among the two more flexible SV, factors SV and Koleski SV, the difference is quite minor. Is now the difference is 6 for 7 variable VAR and a little bit more 12 for 15. So it seems like the factors stochastic volatility model is also very competitive. So now the next thing I want to learn about is what data features, what kind of prior features are important. To that end, I have two benchmarks. One is the symmetric prior, where I basically turn off the cross-variable shrinkage, right? I fix kappa 1 equals to kappa 2. The other benchmark is the subjective prior, this set of values that are commonly used in the literature. And well, my previous paper, I also use these values. So it's quite commonly used and focus on the 15 variable system. So first we compare the symmetric versus asymmetric prior. So the two models, the two stochastic volatility models that allow symmetric and asymmetric prior are the Koleski SV and the factor SV. So for both cases, if you relax the assumption that kappa 1 equals to kappa 2, you get a huge increase in the log marginal likelihood, right? So for the Koleski SV, the difference is about 140 in log marginal likelihood. So that's overwhelming evidence to suggest that the cross-variable shrinkage is present, right? So that's another way to confirm what I show you, that in the first part, I show you the estimation results, and here this is a formal model comparison result. So they are consistent, right? And also true for the factor stochastic volatility. And the other part now is to compare the subjective versus the asymmetric prior. In all of the cases, if you estimate the kappers instead of fixing them a certain value, you also get a huge increase in the log margin likelihood. So it's another way to show that it's beneficial to estimate the shrinkage hyperparameters instead of fixing them at some subjective value. So this is, I think, maybe one of the most interesting slides. So far, I show you that common stochastic volatility model is not as good as Cholesky SV, right? So that's and I repeat myself here just by showing these numbers, right? So if you estimate the common stochastic volatility model, you get negative 2,600 something log marginal likelihood. The Cholesky SV is this value. So the difference is about 173. But we don't know whether it's because of the likelihood, right, or because of the prior. Because the common SV, that doesn't allow you to have cross-variable shrinkage, right? So here I add another version of the Cholesky SV that restricts the kappa to be the same. Kappa 1 equals to kappa 2, turning off the cross-variable shrinkage. And now, if I compare these two, right, it's more fair comparison. Now my prior are more comparable. It's just the difference is the likelihood. Right here, I have one stochastic volatility process, and the Cholesky SV, I have n of them. But surprisingly, maybe for me, I find it quite surprising that now the difference is not so big, right? So the difference is only about 30. But if you just look at the Cholesky SV and allows for different prior, then the difference becomes 100 something 40. So most of the gain seems to be coming from a more flexible prior than a more flexible likelihood, which is a bit surprising. I did not expect to find it. For the factor stochastic volatility, the conclusion is even starker, because if you just look at compare common stochastic volatility, common SV to the factor SV, with symmetric prior, the marginal likelihood actually decreases. So it is actually get worse. So all of the gain, if you compare this number to this number, is coming from a more flexible prior. So that's what I've learned in the second topic about comparing stochastic volatility. Seemingly, in a large VAR setting, having a more flexible prior is more important than exactly what sorts of stochastic volatility specifications you assume. Well, you need to have stochastic volatility, but which type doesn't seem to matter as much. So I have another 8-10 minutes. So I would like to just share with you some of my experience in estimating these high dimensional models, some of the discoveries I have. So I summarize this into 3 different things. One is the equation by equation estimation is very important, which I learned from this paper, Carriero and co-authors. So it's one of these divide and conquer algorithms. It's very useful. Another discovery I find is that it's much faster if you reparameterize the model into a structural VAR, like I show you, into n unrelated regressions instead of using the reduced form. You can estimate the structural form first and then transform everything into reduced form, right? If that is what you want, or you can just use the structural form to compute forecasts. You don't even need to convert to the reduced form. The last point, I just plug some of my algorithms to use some precision sampler, a faster alternative to common filter-based smoother to draw all the latent variables, stochastic volatility or factors. So let me just go through them a little bit. So the first one is probably most significant thing to do if you estimate a large VAR, is that you estimate equation by equation instead of drawing all the coefficients in one block. Basically, you can reduce the computation complexity by 2 orders of magnitude, from O(n) to the power 6 to O(n) to the power 4. So the intuition here is that if you have so the number of coefficients is of the order n to the power square, right? So if you have a big covariance matrix of n squared by n squared, if you do any manipulation to them, right, finding the correctly factor, the best algorithm now is that you need to the complexity is the cube of the dimension of this matrix. So you have n squared of the coefficients, and so to the power cube, you get n to the power 6. But if you do it for one equation at a time, now one equation, you only have the order linear in n, and so you cube it, but you do it for n times, so you get n to the power 4. So essentially, that's the idea there. So there's an issue in the original algorithm in the CCM paper, but we have written a correction to fix it. The bottom line is that the same algorithm, essentially the same algorithm holds. You get exactly the same complexity, maybe a little bit slower. So compared to estimating all the coefficient at once, and you just have a loop to estimate it equation by equation, you can speed up the computation by 10 to 50 times. Right? If you have a larger system, you can not even do the estimation by the whole block because you quickly run out of memory. So another thing you can do to speed up computation is to reparameterize the model, the structural form like I described. It's actually quite good because you can actually parallelize all the computation, right? So if you have access to a cluster in your university, or you use some cloud computing services, you can just send a lot of different jobs, and then at the end, you get all the results and we combine them in your local computer. So you can speed up by 100 times of, depending on how much computing power you have access to, right? But even if you don't do parallelization, just using this parameterization can save you 5 to 10 times computation speed compared to the algorithm I just mentioned in the reduced form. So lastly is that these models, we also have a lot of latent variables. So instead of using common filter-based smoother, which you would require forwards filtering and backwards smoothing, you can estimate generate the whole series, the whole stochastic volatility or factors in one block by using this precision sampler we developed with Ivan. So the idea there is that the covariance matrix of these states, it is full, but the inverse of it, the precision matrix, actually has a lot of structure. In particular, it is a band matrix, meaning that it is a sparse matrix. Not only that, all the non-zero elements are nicely arranged along the main diagonal. And there are fast algorithms to deal with sparse matrix like this. So in terms of computation time, you can, depending on how many states you have, how many observations you have, you can expect 2 to 10 times speed up compared to common filter-based smoothers. So adding all of this is going to be significant. So now if I have a 100 variable VAR with Koretsky SV, and you do all of the things that I said, the estimation time, depending on your computer, but a standard desktop, you might need an hour or two to estimate the model. But if you go a bit larger, then it might not, it might still be too slow, right? So if everything fails, maybe one option is to use alternative to MCMC. So this is probably one of the most controversial slides I have here. So one very promising alternative is variational based. The idea now is that instead of generating samples from the Purdue distribution, you approximate it using a parametric family. It's very much like the adaptive importance sampling I described. Here you have a parametric family and you find one that is closest to the Purdue distribution. So this is the trade-off is that, well, this is not an exact method in the sense that in MCMC, you can reduce the simulation error. If you are patient enough, you just get more and more modules. Here, reducing the approximation error is much more difficult because you need to expand the parametric family. I have some work with Xiaowen Yu, my PhD student at Purdue, very bright student, and we have a better approximation for stochastic volatility in a large VAR setting. So I'm running out of time, I know. So I will just have this slide to conclude, right? So what I've learned so far in my adventure in estimating large VARs is that I found a few features for Minnesota priors. A few features for Minnesota prior are important. One is cross-variable shrinkage. One is you estimate the hyperparameters. And also, maybe you also want to go beyond the Minnesota prior by considering a heavier tilt prior distribution, like all these global local priors. They are all very good. And another message I want to give is that stochastic volatility is important. For macro US macro data, similarly, the Koreski SV is the best, but factor SV is also very competitive. But in these settings, perhaps most surprising to me is that in large VAR settings, seemingly it's more important to have a suitable prior than a more flexible stochastic volatility specification. So thank you very much for your attention. I will just stop here.
Thank you. Thank you very much, Joshua. It was an excellent talk. And also the last bit, you have updated me on all the latest computational developments that you have been working on. So that's all very interesting. We have a discussion open now, and the questions are coming in as I speak. So let me see. From Mike West, we hear that you have given a very nice talk. And he has two sort of more general questions to focus on traditional model assessment for clear distributions for parameters and marginal likelihoods. Echo one step ahead forecast density scores inherently drives a lot of what you find in shrinkage induced forecast performance, forecast methods in your empirical study. So performance, the forecast performance is and should be in the opinion of Mike, addressed modular forecasting and decision goals. So how would you like to respond to that?
Well, so certainly, I mean, in terms of marginal likelihood, sometimes you might not want to use marginal likelihood, right? But I guess for Bayesian, that is one of the most natural thing to do. To use marginal likelihood, but there's of course other options to do it. So you can use information criteria, for example. But I guess all the technical difficulties are always to evaluate the likelihood. So the paper is presented as computed marginal likelihood, but the core is there's a way to evaluate the likelihood. So it can be used to use combined with other information criteria as well.
Okay. Well, Mike has another question, and that is about the TP-VAR and the issues of time-varying shrinkage. Concepts of time-adaptive, smoothly adaptive dynamic shrinkage, including the ability to shrink exactly to zero for periods of time and not for other periods of time, has seen a lot of developments in recent years. Can your favorite priors and computational approaches extend, adapt to relevant and scalable time-varying versions of that?
Oh, thank you very much for that question. Actually, I started to use I started a project with time-varying parameter VAR and in a large dimension setting, And so I was trying to figure out some useful dynamic shrinkage. But then I quickly realized I did not understand enough what's the best even for the constant coefficient, right? So that's I went back to to the constant coefficient setting and try to sort out what are the essential features for them. But certainly, I think now I feel like I know something about the constant coefficient setting. I am more ready to tackle the dynamic setting. Of course, Mike would know there are lots of dynamic shrinkage priors for time-varying parameter VAR. But a lot of them, I think they are developed for generic setting, right? So you don't really know much about, you don't need to know much about the problem, right? It would apply. So what I try to do here is that, well, maybe we need to come up with some relevant prior for these settings, like large VAR. Like one example is Minnesota prior. It has been very successful. So maybe we can incorporate some of those things. That would be very useful.
Thanks. Another question by Florian Huber. And yes, a long question, so I will only take a first part of it. So what are the priors you use on the factor loadings in the FSV, in the factor stochastic volatility model? So do you use shrinkage and a large number of factors?
So I did. So the short answer is they are not hierarchical shrinkage. I probably should have do some of these global local prior as well. But I guess for me is that in those settings, usually I only need a couple of factors, and it is for macro data. So I don't have a lot of factor loadings. So if I remember correctly, they are all Gaussian. But I could also try other hierarchical shrinkage priors.
Yeah, okay. And another question is your comparison with global local shrinkage priors, and you compare them with Minnesota style priors. And the idea is that some impose them on structural equations or structural representations of the model, and that may cause the difference.
Yeah. So that's a very good question. So like I said, it's the structural form is used just as a computational device, right? So of course, it is not order invariant in the sense that if I change the order of the variable, I would get slightly different result. My experience is that if you have some adaptive shrinkage, like those I described, it doesn't seem to matter too much. Of course, if you fix the kappa, right, and if you have the lower rank equation, then you would have more covariates, right? Just by the Kolesky factor, the structure. So in those cases, because the shrinkage is not adaptive, so you might have a bit more different results. So in my experience, it seems to be the case that the adaptive prior can take care of it. Well, I want to say it. I do not mean that the result would not change at all. So it would be a bit different, but it is not significant.
Well, in between all the questions and all the comments, there's also a lot of praise for your presentation. So let me also pass it on to you. And another question from Herman van Dijk is to reduce the dimension of the problem. What about the specification of the structural VARs?
So so here I just use the Kolesky factor, right? So of course, I'm trying to understand the question. I guess I could also do some shrinkage. But another option could be that now I have these covariance as the impact matrix, the elements in there. I could also do some shrinkage there, which is actually what I did also in some other papers. So that would correspond to maybe some special structural VAR, right? So you would be like a lower triangular matrix, but some of these lower triangular elements could be close to zero, right? So that I think that certainly would be useful as well.
Yeah, well, Herman was meaning economic structural equations, so that will reduce the parameter space because of the structural representation of the model. Okay, but that is fine. So let me get on to the next question. Do your results generalize to time-varying parameter VARs?
Well, so certainly, I mean, there are different ways to do time-varying parameter VAR, right? So one way is, I think Florian also mentioned, Sylvia Furich-Schnetter has this non-standard parameterization. So essentially, you just rewrite the time-varying parameter model consisting of two parts. One is the constant coefficient part, the other is some time-varying part, right? So my results would suggest the constant coefficient part, you would need to do a few things, right? And then the other part, well, my result doesn't speak to it. But I guess it would provide a framework. Now you would need to figure out what would be the time varying part that would be the best.
I think maybe one of the final questions, and also a question that I think is very interesting. Is there any evidence, that is the direct question, is there any evidence on how stochastic volatility feeds back into the efficiency of the linear VAR? So how important, basically, and that is my question, how important is sort of the misspecification of the VAR affecting the stochastic volatility part and the choice of the type of stochastic volatility that you consider in the model?
Well, that's certainly very interesting. I don't think I have a good answer to it, right? So Chris Sims has a critique of the time varying parameter VAR. He says, because those models, you don't have stochastic volatility, so you find some nonlinear structure in the mean. But if you include the stochastic volatility, all of them kind of disappear, right? But today we also saw Florian paper, right? They have a kind of different conclusion, right? Because they have this the Bayesian adaptive regression tree, and they have quite nonlinear mean. And if I understand the results correctly, is that if you control for those nonlinearities, stochastic volatility doesn't seem to be very important, right? So I think I don't really have very good answer to that, but certainly you want to have some time variation. But which sorts of time variation to include, I think is very much open to debate at this point.
Okay, and then maybe the final question in the last minute. Is there any work on large dimensional structural VARs and identification in these large models? And is it even feasible?
Wow, that is actually I'm very interested to get into. So I'm working on a few projects. One is factor stochastic volatility to do some structural analysis. The other is just a good old structural VAR and try to work out some identification there. So there are a few attempts, but I think that due to the development of the literature, right? So you first need to figure out how to do reduced form first. And then on top of it, you have some credible identification scheme. And because you also have introduced also quite a lot of nonlinearity. So it's more difficult to do it. But I think it's something I'm working on, and I hope I have something interesting to say in a year or two.
Yeah. No, it was a question raised by Dmitry Kulikov, just for your reference.